Hello, everyone, and welcome to Choosing the Right Water Potential Sensor in 2023. This webinar will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Leo Rivera, whom I will present in just a moment. But before we get started, we do have a couple of housekeeping items. First and foremost, this is an interactive webinar, so we encourage you to submit any and all questions in the questions pane, and we will be keeping track of those for the Q&A session toward the end. Second of all, if you are concerned about missing anything, if you'd like us to go back and repeat anything, do not worry. We will send out a recording of this webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today's presenter will be Leo Rivera, who's been working here at Meter Group for quite some time in R&D, also working with hydrology instrumentation, such as the HYPROP and SATURO. He received his undergraduate and master's degrees from Texas A&M University in soil science, and he's had quite the experience working with soil water potential. I'll let him introduce himself any further than that. So without further ado, we'll let Leo get us started here.
Awesome. Thank you, Brad. And thank you everyone for joining today's webinar. I'm really excited to talk with you all about water potential measurements. It's an area that I really love, and I think it's such an important measurement. So I'm excited to talk about the tools and the advances that we've made in making these measurements. For those of you that don't know me, my name is Leo Rivera. I operate as the Director of Scientific Outreach here, and I also work really closely with these tools. And I'm really excited to get into it. But before we get deep into the details of talking about the tools, I really think it's important to, again, define the basics of what we're trying to measure. And it's really important to look at it in these perspectives. In most environments, most things, and most matter, we have extensive and we have intensive properties. And these two variables are necessary to describe the state of matter or energy in the environment. So we have that extensive variable, which describes the extent or amount of matter or energy. And we have the intensive variable, which describes the intensity or quality of matter or energy. And here are some good examples of that. So on the extensive side, we have volume, water content, and heat content. And they're on the opposite side for those matching parameters. We have density to go along with volume, water potential to go along with water content, and temperature to go along with heat content. And the reason I bring up these last two, heat content versus temperature, is it's really important to understand when I'm thinking about how I feel in the environment and what impacts me, am I thinking about the heat content or am I thinking about the temperature? I'm thinking about the temperature because that impacts how I feel the environment around me. Now, let's think about that in the same terms of water content versus water potential. So let's jump a little bit further and define what water potential is. So here's a very basic definition of water potential. Water potential is the energy required per quantity of water to transport an infinitesimal quantity of water from the sample to a reference pool of pure free water. To simplify that, it's the amount of energy it takes to extract that water from the soil. So think about that in terms of the amount of energy it takes for a plant to access the water in the soil and how tightly bound that water might be. Now, when we think again, going back to this relationship of water content to water potential, again, we have that extensive property related to that intensive property. And this is where soil moisture release curves, which we'll talk a little bit about measuring soil moisture release curves. We're not going to dive too deep into this, but again, this is that relationship of that extensive to that intensive variable. So it's really important to understand both of these parameters. And the soil moisture release curve, which we often refer to as the soil fingerprint, is a really powerful tool for doing that. So just a few more kind of basic definitions here. So total water potential is the sum of its components. And when we think of total water potential, there's four primary components. We have the matrix potential, which is how the water binds to the surfaces or its absorption to surfaces. We have the gravitational potential, which is based on its position within a gravitational field, and the osmotic potential, which relates to the amount of solutes in the water and how that impacts the availability of the water. And then we have the pressure potential, which is the hydrostatic or pneumatic pressure, which is really only something you need to think about typically in saturated conditions. So for today's webinar, we're going to focus primarily on two measurements, matrix potential and osmotic potential. Gravitational potential and pressure potential typically aren't as important in unsaturated conditions, and that's what we're focused on today, is making these measurements in unsaturated conditions. Okay, now that we've gotten all these definitions out of the way, we've broken it down. Let's think about the history of these measurements. And I love this timeline here because it shows how it's evolved over time since 1900, when our earliest attempt was with the Livingston cone, where we had Livingston taking this ceramic cone and actually putting it into the soil, letting it equilibrate, pulling it back out, and making that, weighing it, and seeing how much water it took on, and using that relationship that we talked about, which ceramic has the same relationship, to determine what the water potential was of the soil at that point. From then, in the 1930s, we had some methods developed with the filter paper method and the pressure plate method. And later on in the 1940s, we had electrical resistance methods come along for making water potential measurements in the field. And then later on in the 1960s, we had tensiometry come around. And shortly after that, heat dissipation sensors were introduced. And then in the 1980s, the thermocouple psychrometer was introduced as the first commercially available vapor pressure method for making water potential measurements in the lab. And then in the early 2000s, we started developing capacitance-based techniques for measuring water potential in the field. So we've continued to make all these changes, and the goal has always been to continue to improve and make these measurements better. And if you're really interested in learning more about some of this history, we have a link to a blog post below on environmentalbiophysics.org that I highly encourage you to read if that's something that you're interested in learning a little more about. So this is the past, but where are we going with these measurements? So to understand that, really, we need to understand what the challenges are with these measurements. So here we have a chart that shows all of these different methods. We have laboratory methods on the left-hand side of the chart and field instruments on the right-hand side of the chart. And one of the things that stands out to me about this chart is if you look at the range here, there's really not a method that covers the full range for both lab and field methods accurately. Okay, so this is a big challenge because we really need to understand the majority of this range when we're trying to make these field measurements. So this is one of the biggest challenges, and the goal has been to continue to try and make a better sensor that can cover the full range of water potential. So in this presentation, we're primarily going to focus on field sensors. And there are, we'll touch on lab instruments as well, but we'll do that at the end. But when we think of field sensors, there are three primary methods for making a measurement. We have solid equilibration methods, which was usually done with some type of solid matrix. We have liquid equilibration methods, and we have vapor equilibration methods. And in this presentation, we're gonna talk about primarily the solid equilibration methods and the liquid equilibration methods for the field sensors, because those are the ones that are most viable sensors for use in the field. And we'll focus primarily on capacitance-based, a little bit on thermal conductivity, and we're going to focus on tensiometers. So let's go ahead and jump into the liquid equilibration methods. So the way a liquid equilibration field sensor works is we're going to take some type of, typically a porous cup filled with water, and we're going to introduce that into the soil. And what's going to happen, as you can kind of see from this diagram below, is depending on what the water potential is of the soil, it's going to pull more tightly on that water column within the ceramic. And we can actually physically measure that pull using something like a pressure sensor to measure how much that soil is actually pulling on the water. So what's great is this is a direct measurement of the water potential in the field. And I should specify that this is primarily measuring matrix potential, not really osmotic potential. So tensiometers have been around for a long time, like we showed on that chart, since the 1960s. But they've been fairly similar and had fairly, similar limitations. So the goal with tensiometers, like, well, how can we make a better tensiometer? And that's something that many people have been working on, and we've seen a lot of advances in tensiometer capabilities. One of the biggest things that we've seen, of course, come along is the addition of a digital pressure transducer, which allows us to log these sensors automatically. And then one of the other big changes is minimizing the water column. Traditional tensiometers had really long water columns that oftentimes ran all the way to the surface of wherever the sensor was installed, and we had to make corrections for that water column. So now tensiometers, we've minimized the size of that column so we don't have to make those corrections. And then we've added external refilling with things like capillary tubes. That way we can still refill them from the surface, but we don't have to have that big water column that we need to make corrections for. And a really great change is because we've started utilizing digital pressure sensors, we can now measure both positive and negative pore pressures, which is fantastic because it allows us to utilize these things for applications like slope stability, where that transition from a negative to a positive pore pressure can indicate that there's a potential for slope failure. So that's been a big advancement there. And then with some of these tools like the laboratory tensiometers, we've also been able to extend the measuring range. Um, Traditional measuring ranges for tensiometers is typically down to about minus 85 kilopascals because the water cavitates. But with some of these newer tools, we've been able to delay that cavitation or that boiling point, which allows us to go beyond the traditional minus 85 kilopascal range, potentially up to minus 250. And in some cases, we'll talk about high capacity tensiometers here just briefly, even beyond that. So let's go ahead and jump into just briefly cover high capacity tensiometers as well. So in more recent time, we've seen advances with tools that are called high capacity tensiometers. And these are sensors that are capable of directly measuring very low water potentials. And these sensors consist of a high entry ceramic filter, a pressure transducer, and then a protective housing, of course, to protect the sensor. And these sensors have to be degassed under really high pressure. You can see an example of what a high capacity tensiometer can look like on the right hand side. Typically they have really small water reservoirs, and you can see that ceramic membrane and where the pressure sensor is. These are really powerful tools because you can push them beyond the normal measuring range. We've seen examples of these measuring down to minus 3,500 kilopascals in the field, or even further. But the challenges with these sensors, there's a couple. They're not commercially available yet. We've seen some attempts at it, and they're not there yet. And the other challenge is these sensors have to be degassed under really high pressure, and that means when they decavitate in the field, you have to pull them back out and degas them again under really high pressure, which isn't super feasible when you're in the field and you're trying to refill these. So really powerful tool. I'm really excited to see the future of where something like this goes, but they're not quite there yet. So let's briefly just touch on some of the pros and cons of liquid equilibration sensors. Advantages of these sensors: they have the highest accuracy of any sensor in the wet range, and they can measure positive pore pressures. Disadvantages: they're typically limited to the water potential ranges from 0 to minus 90 kilopascals, minus some of the examples that we talked about, the high capacity and some of the extended range sensors. And tensiometers, because they degas, have significant, or need to be degassed when they cavitate, have significant maintenance requirements along with them. So powerful tool, incredibly accurate, but they do have some limitations. So now let's move on and let's talk about solid matrix sensors. So the way a solid matrix sensor works is we'll have a solid matrix of some sort, whether it's ceramic or some other type of porous medium that is going to be put into the soil and equilibrated with the water potential of the soil. And so depending on where that point is, where that water potential point is, the ceramic is going to take on more or less water. And what we can do is use that relationship of the ceramic to give an indirect measurement of water potential. And so you can kind of see an example of what that curve looks like here. And so it can be a really powerful tool. Let's talk about some of the different methods that we have available. So we have, so first we're going to focus on the thermal-based methods. Again, we have a standard matrix. In this case, they're a ceramic-based matrix. And the water content of the matrix is measured with an induced temperature, by a heat pulse that's inducing a temperature rise in the ceramic. And depending on what that temperature rise looks like, we can determine how much water is being held in the ceramic. And we then use this relationship, that temperature rise, to matrix potential. And these sensors need to be calibrated to output water potential based on these ceramic characteristics. They don't typically come calibrated. And so to really hone these in, they need to be calibrated to make them a little bit more accurate. But these are really powerful tools to make these measurements. So thermal sensors have been around for, since the late 1970s, or since around 1970s, 1960s. But they were great, but we wanted to find ways to make them better. So that's when we started working on capacitance-based techniques. One, the capacitance-based sensors use less power and can be made less, a little bit lower cost. So again, we still have a standard solid matrix, a similar ceramic, actually the same ceramic that's used typically on the thermal sensors. That again is equilibrated with the soil. The water content of that matrix is measured with capacitance-based technology, and you can see how that field is confined into the ceramic. And we then have taken these sensors, and we have that same relationship of the water potential and the water content of the ceramic that we're making this relationship. Now, one of the changes with these capacitance-based sensors that has really been the big improvement has been the calibration process and the way these sensors are calibrated. And so having an individually calibrated solid matrix sensor has really improved the accuracy of these sensors and the ability to use multiple sensors and have them compare nicely with each other. So capacitance sensors, like we talked about, were brought about in the early 2000s. And of course, one of the challenges with those sensors, again, was still the limited range. So you can see here that chart that we showed earlier. And you can see here where we have the Teros 21 and the MPS6 and also the heat dissipation sensors, where they have that limited range to about from -10 to about minus 100,000 kilopascals approximately. And we needed to find ways to continue to try and expand that range. And so we actually worked on the generation 2 of those sensors with new circuitry, which actually allowed us to extend that range up to saturation. And so again, we're continuing to try and make advancements in these measurements. And one of those key advancements that we need to make is the range of those sensors and what they can measure. And so that's been one of the biggest advancements that we've seen come along with these sensors, is improving the range and still having an accurate sensor in that range. Now, they're not as accurate as tensiometers. Nothing is going to really compare to that. But we have a no maintenance sensor now that allows us to measure a much broader range of water potentials in the field. So let's summarize again some of the advantages and disadvantages of solid matrix sensors. Advantages: no maintenance is needed for these sensors. They don't have to fill them. They're really easy to use for long-term deployments. They have a much larger sensing range, like we just covered. And what's great about this is these sensors cover the plant available range, which is one of the most critical ranges that we need to cover in the field, especially if we're trying to do drought stress studies or anything along those lines. That's been the biggest, it's such a key factor there. And then now with the improvements in the calibration techniques, when these sensors are calibrated, they have really good accuracy as well. So that's been a big change there. Disadvantages: obviously, the accuracy is dependent on a calibration, so you need to make sure that you either are getting your sensor calibrated or you're getting a sensor that comes calibrated. Traditionally, they've had limited wet-end performance, but we've seen improvements there with the Gen 2. And in some cases, we've seen some temperature sensitivity because there's so little water held in the dry range. But we've also seen improvements with some of the methods that we've seen for making those corrections, and that's something that we can touch on later, or in and maybe with some future content, but using some of the methods that have been shown to make those corrections. So I think one other area of advancement that we need to cover is not just in the sensor, but how we install the sensors. I think with any sensor that we have out there, the quality of your measurement is dependent on a quality installation. Water potential measurements are no different. Water potential data is absolutely critical, or is actually absolutely dependent on a good installation. And so now we see tools like what you see here with our borehole installation tools that allow us to install the sensors, ensuring we have good soil contact while minimizing the site disturbance, and allowing us to put these sensors at much deeper depths without having to make large holes to get them into the ground. And we can go down to 2 meters and beyond if needed. And this is great because it's going to limit preferential flow, it's going to limit site disturbance, and it just makes the installation process easier overall. So this is another key area that I think we've seen advances in, is just the installation capabilities as well. Okay, so like we said earlier, I did want to briefly touch on laboratory methods. Laboratory tools are still absolutely critical tools for helping us make have an understanding of the relationship between water content and water potential in soil. And we've seen big advances in the tools that allow us to make these measurements. Here you can see an example of two of the techniques: the evaporation method, which utilizes tensiometers and a saturated soil core, and we're measuring that as it's evaporating to get the wet end of the soil moisture release curve. And you can see that here in the chart in the middle. That left-hand set of data comes from a tool like this. And then with the development of tools like the dew point techniques, like things like we see in the WP4C, we are able to hone in on the dry end of the soil moisture release curve. And we've continued to push these tools as well. But really, we've made improvements in the tools, but the other improvements, I believe, really come from our understanding of the curves that we're generating with these tools. So here's an example of a soil moisture release curve that's generated with a tool called the vapor absorption analyzer, where we're automatically doing the wetting and drying curves of the dry end of the soil moisture release curve. And you can see all these different soils have very different curves, and you see different hysteresis loops, sizes of the hysteresis band within these soils. So what is that telling us? What additional information can we get from the soil moisture release curves? And that's an area that we've seen even bigger strides and advancements in. And we've seen improvements, or we've seen research showing how we can utilize these curves to get additional information like the shrink swell capacity of soil, the cation exchange capacity of soil, and the soil specific surface area. Here on the chart on the left, you can see an example of where we were using the slope of the soil moisture release curve to relate to the shrink swell capacity of soil. And we've seen additional studies showing further and further refinements of this, and that's improved our ability to make these understandings. So here, I just wanted to throw up some of these references if you wanted to dig into that a little bit more. There's a big growing body of work on utilizing these soil moisture release curves to better understand these properties. And so I highly encourage you to take a look at these publications. This is really an area that I'm extremely excited to see grow and see what we can learn from the soil moisture release curves, because there's a lot of information that lives within that curve that can help us better understand and better characterize soil properties. So one last thing that I want to touch on is some future tests that we're working on. One of the things that we really want to understand is the effects of a confining load on soil hydraulic properties. Most methods are, unless you're a geotechnical engineer and you're using some of the other tools that they use, but most of these methods are unconfined soil samples. And what we've seen in the literature is that confining loads or constant pressures can and will impact soil hydraulic properties. So how can we characterize these impacts with some of the conventional tools like the HYPROP? And this is some of the work that we're working on, trying to better understand, and I hope to present more on this in the future. But here you can see an example from one of our pilot studies where we induced different confining loads to the same soil and measure the soil moisture release curve of that soil. And you can see that this actually collapsed the retention curve. So we're going to continue to dig into this, run different soils, and see what we can learn from these tools and see if we can develop a tool to help us characterize this with some of the traditional methods. So this is something I'm excited to keep working on. And lastly, just want to conclude, there's a lot of tools available to measure water potential. I think it's absolutely important that you keep in mind the measurement range for your application and what's most critical to you. If you're trying to understand water movement or hydrology, or those types of things, you might be more interested in a tool like a tensiometer, because that's going to give you the accuracy that you need to make those understandings. If you're more interested in plant stress, then you probably should lean more towards the solid matrix type sensor that's going to better cover that range. And installation is absolutely key in getting a quality water potential measurement. So I think it's really important that we keep that in mind as well. And we really need to continue advancing the capabilities of these measurements. We need to keep working on sensor capabilities and improving that. And that's something that I know we will and other people will continue to work on. And we need to improve our understandings of the models and how we can utilize this information to better characterize soil properties. With that, I think we can go into questions.
All right, thank you, Leo. So yeah, we have, we'll take questions for about 10 or so minutes here. We've got a few questions that have come in already. Thank you for those. Again, there's plenty of time to submit your questions, so feel free to add them to the questions pane. We'll try to get to as many as we can before we finish. If we do not get to the ones that you have submitted before we finish here, we will have them recorded, and somebody, including Leo, will be able to get back to you via email to answer your question directly. All right, so we do have a couple of questions just kind of on the basics of water potential. And one of them is asking about positive water potentials. Is that something that we only see when we're in, measuring in solution? Are there other examples of positive water potentials?
Yeah, so absolutely. And we touched on the total components of water potential, and the pressure potential is one of those components. Typically, you're only going to see that in saturated conditions. And what typically is inducing that positive pressure is the height of the water column above that. So you'll typically see that, as the water table is rising, for example, we'll see increased pressure potential, which is that positive component of the water potential. Now, I have seen that there are times where you can have positive pressures even though the soil actually isn't completely saturated, and that has to do with more other impacts around, whether it's increased pressure from loading or if there's other things going on. But typically, it's coming from saturated conditions and the water table that's inducing that pressure.
Okay. The other one we've talked often about, and you've mentioned about with these water potential matrix potential sensors, that they're soil type agnostic, meaning that there's no change in accuracy or measurement from soil to soil. Is there any effect? Someone's asking if there's any effect in the type of, for instance, like field crop or cover crop or plants above or things like that. Does that affect water potential in any way?
Yeah, that doesn't. It's not going to impact the sensor, but what those crops do impact is the properties of the soil, and I think we're seeing this term dynamic soil properties coming around quite a bit, and those are things that impact how the water is retained in the soil. But what's great is the sensor is going to measure that impact. So that's something that you're trying to characterize. How do cover crops impact how water is retained in the soil. The measurement's not going to be impacted by it, because the measurements, again, is just water potential. It's a energy state. But you should see, for example, if you're measuring water potential and water content together, what you would probably see is a change in that relationship of water content and water potential in that soil, because of the way that those cover crops or whatever it is impacting those soil properties.
All right. This next question is actually asking about calibration of the sensors. They're saying, what happens if there's what happens if it's calibrated wrong, or who does the calibration? Does it need to be does it need to be recalibrated from from install to install, from soil type to soil type? Can you go into a little bit more depth about calibration?
Yeah, absolutely. So that's a really good question. And it depends on the sensor type, obviously. But for example, some solid matrix sensors have that are based on some of the electrical resistance methods, have a gypsum inner core that's being used in that measurement. Over time, that gypsum core can degrade, and that means your calibration is going to shift as that gypsum is degrading. So a sensor like that, you absolutely will need to keep track of how that's changing over time, and you will likely need to recalibrate or replace those sensors over time. The other solid matrix sensors, like the thermal and the capacitance based techniques that we talked about, are based on are utilizing a ceramic that is very field stable. It is not typically going to break down in the majority of conditions, and because of that, they really don't need to be recalibrated. Obviously, the thermal sensors, you'll need to do a calibration because they don't come calibrated, but the sensors that come calibrated from factory uh, don't need to be recalibrated over time. Obviously, if something happens, they get physically damaged. That's a different story. But they should be very field stable.
All right. Okay. Hopefully that helps. We did have a few other questions based on or asking about calibration. If those didn't help, then we can get back to you and answer your question directly as well. You talked about the relationship between water potential and water content. And so there's a couple questions in here asking about that relationship with soil moisture release curves and other things. One of them is asking if you can just get water potential from a soil moisture release curve. Do you necessarily need to install those water potential sensors? Could you just use volumetric water content sensors, something along those lines?
Yeah, it's another really good question, and that is a common approach because the water content sensors are easier to use. They're typically easier to install, um, and uh, and they you don't have to worry about the range considerations with the water content sensors. So it's not a bad approach, but the challenge with that approach, and this is something you need to keep in mind if you're doing this, is did you make your moisture release curve on a wetting or drying curve? Um, and uh, so that's one of the biggest things to consider because we know there's hysteresis present in the soil. So if you made your moisture release curve on a wetting curve and you're on a drying curve, then that relationship actually shifts a little bit. And it depends on how important it is that you have a little more accuracy in that measurement. So there's risks there. The other risk is, again, we talked about these dynamic soil properties. Over time, that relationship can change if you're making management changes to the soil that's going to impact these soil properties. And so that curve might not actually represent what's actually happening in the soil anymore because these properties have changed and that relationship has shifted. So that's another area where just uh, these are areas that I want you to just think about before you choose to use one method or the other. What level of error and risk are you willing to accept in these measurements as you're trying to make them? So obviously we prefer direct measurements because again, we know exactly what's happening. Um, but people use this approach all the time.
So along those lines, somebody's asking about how does or can organic matter affect water potential within the soil, and also then would that possibly affect your soil moisture release curve that you were doing either in the field in the lab?
Yeah. Yeah, absolutely. Organic matter impacts the way the water is retained in the soil. Typically, when you see an increase in organic matter, we see an increase in the retention capabilities of the soil, the ability of the soil to retain water, and so it does impact that soil moisture release curve. Now, the sensor itself can physically measure, again, because it's an energy state. We're still directly measuring water potential. So even if we see an increase in organic matter, we're still measuring what the water potential is of the soil. Now, what we're going to see a change in again is that retention, what that curve looks like. So that relationship between water potential and water content. And that's really where you're going to see the shift. And so that's, again, an area that, as we see these properties changing, is the relationship is going to change. But the water potential sensor itself is still going to directly measure water potential.
Along those lines as well, somebody, or I guess maybe on the flip side, somebody's asking about using water potential sensors in soilless media. Can you give some insight into that?
Yeah, that's a good question. Soilless media has different challenges, and the biggest thing there is it retains most of its water in the really, really wet range of the salt moisture release curve. Typically, when we make salt moisture release curves on most soilless medias, the majority of the water is retained in the 0 to minus, let's say minus 30 to be conservative. We see it tighter in some soils, but 0 to minus 30 kilopascals range, maybe a little bit beyond that, down to 60 kilopascals, depends on the makeup of the media. But that challenge means that you need a sensor that's going to work well in those really wet ranges. And so that's really where the tensiometers are much better tools to make water potential measurements, because it's such a wet, it retains so much water in that wet range that if you try to use any other tool, it wouldn't really give you very good measurements. So yeah, that's the biggest challenge with soilless media.
How about, I'm throwing out all these different applications. Someone's asking about dealing with soil in freezing conditions. How does that affect or being able to work with water potential sensors?
Yeah, another really good question. Freezing conditions are going to impact pretty much all of these methods. Once the soil water freezes, you're not really going to be able to measure the water potential with a traditional sensor. Now, having said that, there is a relationship for every degree below freezing. So if, say, for example, you have one of these sensors that also has a temperature sensor, I can't remember what the exact conversion is, but for every degree below freezing, there's a relationship between that and water potential. And it's a pretty significant drop, as you can imagine. But so you can actually use that temperature measurement to infer what the water potential is in freezing conditions. Now, having said that, tensiometers have the risk of being damaged in freezing conditions because that water will expand in the ceramic. So if you have a risk with tensiometers, you're going to want to make sure that you empty freezing with tensiometers. You're going to want to make sure that you empty the water out of the ceramic reservoir, out of the water reservoir, so you don't damage those sensors.
All right, we're coming up to the end of our time here. I think this might be our last question. Again, thank you to everybody who's submitted their questions. We will be able to get back to you with an answer via email if we do not get to your question here. One of these questions here is also going back to the beginning of your presentation when you were talking about the correlation or analogy between a temperature on a thermostat and versus water potential. And so they're trying to say, okay, well, we've got like if we're dealing with temperatures, say within our house, we know the air moves around our house freely or relatively freely, and so that temperature then can be transmitted from room to room without the house. It's a little bit different within the soil, with the water movement within the soil. So how do we get around, or how do we deal with moving from taking a spot measurement or having a single sensor in one spot and then trying to correlate the entire field's water potential? How do you get around a situation like that so we can really measure the quote unquote how the soil feels when it comes to water potential?
Yeah, that's another excellent question. There will always be challenges in the field with spatial variability, and this water potential is not. This is one area where it's still going to be impacted by spatial variability because it depends on how the water moves through the soil, especially if we have rain and if there's preferential flow paths and those types of things. So there is definitely going to be some spatial variability in the water potential measurement and trying to relate that. So it has similar challenges just as the water content measurements do to how spatially variable that can be. It's really important that you understand what your zones of variability could be. It could be soil type dependent. It could be based on the topography of the soil. So it's important to understand those things. And I spent quite a bit of time myself trying to characterize some of this variability using tools like an EM38 device to go out and measure the change in EC to try and infer what some of these zones might be, and so where this variability might coming from. But the really cool thing about water potential as well is water potential is the governing factor that 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 governs how water moves and how things equilibrate in the soil. So over time, if there's not any big changes in conditions, if we don't have any additional irrigation, water potential is going to want to equilibrate over time. So if you were going in between wetting events, you might see that as more time goes on, some of those zones of variability might decrease, especially if they're similar soil type. Not really soil type, actually. Sorry, not similar soil type. Just over time, that energy state wants to equilibrate. So as long as there's not any factors that are going to limit water movement and transfer between areas, it will equilibrate, and you'll see a decrease in some of that spatial variability. But again, with all of the impacts that like water movement has and rain and preferential flow, you'll still see some of that spatial variability. But with the cool thing is that it does try to equilibrate over time. And so that's, yeah, water potential governs so many things. So it's really what makes it a fun measurement.
All right, that's going to wrap it up for us today. Thank you again for joining us. We appreciate all of your questions, and we hope that you enjoyed this discussion. Please consider answering the short survey that will appear after this webinar is finished, just to let us know what types of webinars you'd like to see in the future. Also, for more information on what you've seen today, please visit us at metergroup.com. Finally, look for the recording of the presentation in your email, and stay tuned for future meter environment webinars. Stay safe and have a great day.